Hey everyone, welcome to our final project demo. This is Team VES NLP, I'm Tiger, and today we're actually going to try to make a turkey dinner in our virtual smart kitchen. So we're also going to try to demo some of our project's feature and capacities while we're doing that. So as the first step, I'm going to try to grab a tray from this cabinet. Throughout the semester, we implemented a couple of different ways for the user to interact with the devices in the virtual space. And one of them is by directly saying the device's name. So for example, in order to open this, I can say, open cabinet, and it's going to open for me. Alternatively, I can say something even simpler, and the NLP engine is going to be able to predict that for me. So, for example, I can just say something even simpler like close this. Great. And then since we're actually predicting the user's target object using the cosine distance and the Euclidean distance, the user actually does not have to be looking directly at the center of the object. And the gaze point is indicated by the blue dot that you can see on the screen. So I can even move closer to maybe the top left corner here and then try again. Open. Yep, and that still works. Great, so now I'm just gonna grab this tray and then start making our dinner. Here we go. Close. Great. Now we have our tray, so let's grab a turkey from our fridge and let's open the fridge door first. Open. Great. Oh, our turkey is in there, so let me just go ahead and grab that. Here we go. Put it in my tray. Great. Now, oh, I'm not gonna forget closing the fridge door here. Close. Awesome. And sometimes, the user doesn't even have to be looking, make sure that the gaze point is actually on the object. So, for example, over here, maybe, this turkey maybe doesn't look too bad for a microwave to cook. So let's try that. Open. Yeah. So as you can see, even when the blue dot, which indicates the gaze point, again, when it's not even on the object, it still works. But maybe this is too big for a microwave to cook. So let's close this. All right. Let's actually still put this in an oven. So let's try that. Open. Great. All right, before I put this in, I'm actually going to start the oven's preheat. So turn this on. Oh, it lights up. As you can see, that's a new animation that we've added. So now I'm just going to carefully put this tray of turkey in my oven. Here we go. All right. And now it's ready to cook. So close. Great. While we're waiting for our turkey to cook, we have some slides that covers the progress that we've made since our midterm presentation. So let's do that while our turkey is cooking. So a couple of things that we changed since our midterm presentations. First, we changed from using local user position to global user position in Unity. Since we've been collecting global device positions, so now there is no discrepancies between the two. We've also updated our cosine distance calculations, and after these changes, we've recollected more data for these three cabinets: the dishwasher, oven, microwave, and freezer. And now we total at 27,396 pieces of data. So moving on to the results of our machine learning models, the multiple linear regression model now converges around epoch 1500, and the best accuracy we've achieved is about 97%. And for the naive Bayes model, it now performs with an overall accuracy of 90%. And for the decision tree model, the best accuracy that we achieved is about 97.89%. It is a little zoomed out, but if you look at it, the decision tree model, in fact, weights the spatial information, namely the cosine distance and the Euclidean distance, a lot heavier than the other inputs. So in order to test our overall workflow, we conducted a series of end-to-end evaluations. Since we're using the built-in speech-to-text function in Unity, and our NLP model has been performing relatively well and stable, we have decided to focus the evaluation on the machine learning models. We performed open and close actions on the 7 targets in the VR space, as shown here: the 3 cabinets, dishwasher, oven, microwave, and the freezer. Now, we select these objects mainly based on if they allow us to test the robustness of our target prediction. An example here will be the freezer and the dishwasher selection, which are very close to each other spatially, and they can both be open and closed, so the availability list cannot be used to distinguish the two. We also tried to angle at 5 different gaze points on each object, namely the object center, to the left of the object, right, top, and bottom. And by doing these, we're trying to eliminate the user bias, since generally the user would look towards the center of an object when they try to interact with it, but the definition of center could be different for everyone, so we do want to check on that. And here are some of the results of our evaluation. As you can see on the left, that is our server-side outputs. For every time the user utterance comes in, there are 3 outputs from our 3 different models. And on the right-hand side, the rows denote the object that we're testing on, the gaze point position and the intent, and the columns are correspondingly the MLR output, decision tree output, knife base output, and our final voted output. A 0 in the table will mean the model made an incorrect prediction, and a 1 means the model was correct. So you can see that in the very bottom, the testing accuracy of each of these 3 models. They're about 0.85, 0.94, 0.97. And the voting strategy actually worked surprisingly well for our cases. Among the 70 cases that we performed, the accuracy of the final voted prediction is 100%. So that's pretty much it for the slides. Now let's go back to the unit. All right, so that's pretty much our progress since the midterm presentation. And now let's see if our turkey looks ready. Let's see. Oh, that looks delicious. All right, let's get this thing out of here. Open. Looks perfect. All right, let me just carefully grab this tray from the oven. Here we go. Oh, look at that. Look at that. That looks absolutely delicious. All right, everyone. This turkey looks beautiful. Oh my God. All right. Oh,